Cloud and AI architects must practice defensive design and governance to stay out of trouble, wrote David Linthicum in his piece, When Cloud AI Lands You in Court. Here he delved into a telling debacle involving the AI-powered chatbot from Air Canada, which misinformed passengers regarding bereavement fares, a classic case of digital misinformation with real-world consequences. The chatbot suggested that the passengers could retroactively apply for bereavement fares, despite the airline's bereavement fares policy contradicting this information. Of course, the link to the policy was provided in the chatbot's response. However, the court found that the airline failed to explain why the passenger should not trust the information provided by the company's chatbot. This story serves as a vivid wake-up call about the dangers lurking within poorly managed AI systems. So what's the safety net here? Defensive design. This proactive strategy is akin to wearing a seatbelt in a car. You don't plan to crash, but you are securely prepared for the possibility. In the realm of cloud and AI, it's about setting up fail-safes and safeguards to anticipate and neutralize issues like misinformation, bias, and potential legal entanglements before they spiral out of control. Linthicum nails it when he says, generative AI has the same limitations as all AI systems. It depends on the data used to train the model. Crappy data creates crappy AI models. Worse, you get erroneous responses or responses that may get you into legal trouble. It's important to acknowledge the limitations inherent in these AI systems and understand that at times they can exhibit what may reasonably be called stupidity. This stupidity can put you out of business or get you sued into the Stone Age. The takeaway? Investing in quality data is not just a chore. Providing solid training data for AI models is critical investment in the health and legality of AI applications. In essence, defensive design isn't just about dodging legal bullets. It's about creating robust, reliable systems that stand up the scrutiny and deliver as promised without nasty surprises. Architects can craft AI systems that not only perform well, but also play it safe on the legal and ethical fronts when they focus on thorough testing, meticulous documentation, vigilant auditing for biases, and considering ethical implications. This strategy isn't just smart, it's essential for anyone eager to sidestep legal entanglements and unfavorable outcomes. To bolster the robustness and reliability of systems, organizations often integrate a complementary strategy, security by design. This method addresses a broader range of risks, including security vulnerabilities, by ensuring that security measures are woven into the fabric of system design and development from the outset. Security by design is about building systems that are fundamentally tough against cyber threats and unauthorized intrusions. Embedding security deeply into the system architecture cuts down the risks for security breaches and data compromises. This shift towards enhanced security is underscored by the increasing adoptions of memory-safe programming languages within the cybersecurity community. In December 2023, a pivotal moment unfolded as a coalition of global cybersecurity powerhouses, the US agencies Cybersecurity and Infrastructure Security Agency, CISA, NSA, and FBI, the Australian Cybersecurity Centre, HCSC, the Canadian Centre for Cybersecurity, CCCS, the British National Cybersecurity Centre, NCSC UK, and the New Zealand National Cybersecurity Centre, NCSCNZ, and Computer Emergency Response Team, CERT-NZ, issued a groundbreaking call to action. Their collective plea, articulated in the paper The Case of Memory-Safe Roadmaps, serves as both an alert and a guide toward a more secure digital era. Their message delivered in a meticulously crafted paper is both a warning and a roadmap to a safer digital future. They advocate to a transition to secure programming languages like C#, Go, Java, Python, Rust, and Swift. The rationale? Memory management mishaps, specifically buffer overflows, And improper memory allocations are fundamental weak spots in software security. These issues may seem technical and obscure, but they are critical vulnerabilities that hackers exploit to penetrate systems, often with catastrophic results. Languages like C and C++, which have been mainstays of software development, are particularly susceptible to these vulnerabilities. So, what does memory-safe programming look like in action?
What does a memory-safe programming language mean?
Let's bring this to life with coding examples that illustrate just how these memory management blunders can be exploited and why transitioning to memory-safe languages is more than a mere precaution. Imagine this. Jack, a programmer, taps away at his keyboard, crafting seemingly harmless C program. C, known for its power and speed, is akin to a high-performance sports car. It's exhilarating, but comes with its risks, especially when it comes to managing its memory. Let's dive into Jack's code. Jack's program asks for your name and greets you. Simple, right? However, beneath these straightforward interactions lurks a significant threat: the strcopy function. It blindly copies the input to a buffer without checking its size. Enter the hacker, Bob's strategic move. Meet Bob, the hacker. He noticed that Jack's program doesn't bother to check the length of the input. Seeing his opportunity, Bob concocts a malicious input that exceeds the buffer's limit, embedded with a devious snippet of code, a payload. When Bob feeds this input to Jack's program, the payload overflows the buffer and spills into adjacent memory areas. This overwrites crucial control data, such as the function's return address. With precise manipulation, Bob redirects the program to execute his payload, effectively taking control. Visualizing the attack, this is what happened in memory. Buffer, 10 bytes. Saved return address, malicious code overwrites here. The consequences? Such exploits could open the door to unauthorized system access, data breaches, or even remote control over the affected machines. A hacker's trifecta of chaos. The lesson: this scenario underscores the dangers posed by non-memory safe programming languages. In languages like C, the onus of memory management falls heavily on the programmer. A single lapse, such as neglecting to check buffer lengths, can open floodgates to cyber assaults. In contrast, memory-safe languages like Python or Java handle memory management more cautiously, which reduces such vulnerabilities. While they might not offer the raw speed or control of C, they add a critical layer of safety, much like airbags in a car, that shields against such threats. Understanding these risks is vital. It influences not just how we write code, but also how we architect entire systems, with a keen focus on security and resilience in our interconnected digital realm. Real-world cybersecurity incident. To illustrate the more real-world consequences of buffer overflows, let's consider some simplified scenarios. Although these examples are distilled for clarity, real attacks can be more complex and may involve additional tactics and techniques. Unauthorized access. Imagine a program that authenticates user based on their username and password and has a buffer overflow vulnerability. This program might be compromised, which allows hackers to bypass security checks. The attack scenario. A hacker can exploit the get function used for reading the password. By providing an excessively long password, they could overflow the buffer and manipulate the program's control flow to always grant access, bypassing actual authentication check. Data breaches. A buffer overflow could also expose sensitive information, as in the following example. The attack scenario. A hacker could exploit the buffer overflow to read out-of-bounds memory areas where sensitive data might be stored, which leads to a data breach. Remote control. For remote control, hackers could use a buffer overflow to execute arbitrary code on the affected machine. The attack scenario. Using a carefully crafted input, a hacker might overflow the buffer and overwrite the return address of the process command function. If they replace it with the address of their own malicious code, perhaps injected as part of the input, they can gain control of the program which potentially leads to remote execution of arbitrary code. Python and the paradigm of memory safety. Switching our focus to Python now. Unlike C and C++, this language automates memory management. This reduces the risk of memory-related errors. Python's garbage collector ensures that memory is efficiently managed without manual intervention. Final thought. As we close the discussion about defensive design and security by design, it's crucial to remember that the software we craft today sets the stage for the tech landscape of tomorrow. Whether we are dealing with the intricacies of AI systems or the foundational aspects of memory-safe programming, the stakes are higher than ever. Like the great architects of the physical world, the durability and safety of our structures, our codes and systems must endure and secure against the tremors of change and the assaults of unforeseen threats. Defensive design and security by design aren't just methodologies. They are imperatives that demand the utmost attention and action. A bridge collapse and a security breach both have far-reaching impacts. The one disrupts lives and the other endangers data. Both are essentials to the fabric of our society. Let's engineer our systems with foresight, shall we? Excited about diving deeper into the world of software architecture? This video is just the beginning. Check out my Udemy video course on software architecture, where I explore these concepts further and dive into real-world challenges. The link to the course is in the video description below. And here is a bonus. Subscribe to my newsletter and you will get free access to all my courses. If you found this video helpful, don't forget to hit the like button and subscribe to the channel for more updates and tech insights. See you next time.